Let's look at some more theorems. In an equation with real coefficients, complex roots occur in conjugate pairs. Okay, let's prove this. Let f and x equal to a naught plus a1x plus a2x square plus and so on up to an k, where a naught, a1, a2 and so on up to an are real. Now let z equal to a plus ib be a root of fnx equal to 0. So that is fnx fnz equal to 0. So looking at fnz star will become fnz star is equal to a naught plus a1z star plus a2 z star square plus and so on up to an z star n. Now we know z star m is equal to zm star. So therefore fnz star is equal to a naught plus a1z star plus a2z square star plus and so on up to an z to the power of n star. Yes. Now since a naught, a1, a2 up to an are real, that implies that an star is equal to an. That means the conjugate of a real number is the real number itself. So therefore fnz star is equal to a naught star plus a 1 z star, this also will be star, conjugate of a1 conjugate of z plus a2 conjugate z square star plus and so on up to an star zn star. Also we know w star z star is equal to zw star. So therefore fnz star would be equal to a naught star plus a1z star plus a2z square star plus it will go on till anzn star. Now we know w star plus z star is equal to z plus w star. So therefore fnz star would become equal to a naught plus a1z plus a2z square plus anzn star, which implies fnz star is equal to fnz star, which implies that fnz star is equal to fnz is equal to 0. We have already seen here, since it is one of the roots, z is one of the roots, so this will become 0 star since fnz is equal to 0, which implies fnz star is equal to, okay, that is one way of proving this. Now let's look at another proof. Now let a plus ib be a root of fnx equal to 0, which implies x is equal to a plus ib, since a plus ib is a root, which implies x minus a is equal to ib. Now let's square both the sides, so we get x minus a square is equal to I square b square, and let's bring that to this side. X minus a square minus I square b square is equal to 0. Now let q be the quotient and rx plus r prime be the remainder when fn x is divided by x minus a square minus I square b square. Yes, remember a plus ib is one of the roots. It is given to us. So if we divide the function or the equation by this, we would get the quotient and a remainder if it is there. So which means we can write this as x minus a square minus I square b square times the quotient plus rx plus r prime, the remainder. Now this is ib the whole square, right? So this becomes a square minus b square, which is nothing but a plus b times a minus b. So this can be written as x minus a minus ib and x minus a plus ib times q plus rx plus r prime. Okay, so now let's substitute the given root fn a plus ib is equal to, now we substitute x by a plus ib. So a plus ib minus a minus ib, a plus ib minus a plus ib times q plus r times a plus ib plus r prime. Now here if you notice, a cancels, ib cancels, so we are left with 0. 0 times this is 0. So this becomes 0 plus r times a plus ib plus r prime, and this would be equal to 0 because this is a root. Okay, so which implies r a plus ib plus r prime equal to 0, r a plus r ib plus r prime equal to 0, which implies r a plus r prime plus rib equal to 0. Now let's equate real and imaginary parts. Okay, so we have ra plus r prime is equal to 0 and rb equal to 0. Now remember, b is not equal to 0, right? So therefore r has to be equal to 0 for this to be true. Now if r is equal to 0, that means 0 plus r prime equal to 0, which implies r prime equal to 0. So therefore remainder is 0, which implies fn x is equal to x minus a plus ib and x minus a minus ib times q is equal to 0. Remainder part is 0. So therefore fn x disappears when x is equal to a plus ib and x is equal to a minus ib, right? So a plus ib means this will disappear. A minus ib means this will disappear. Therefore, a minus ib is also a root of fn x equal to 0. Two ways in which we can, or we have proved. Let's look at the next theorem. In an equation with rational coefficients, irrational roots of the form a plus root b occur in pairs, plus or minus, occur in pairs provided b is not equal to 0 or a perfect square. Okay, so given for f and x equal to 0, a plus root b is a root. Now we have to prove that a minus root b is also a root. Okay, so since a plus root b is a root, we can say x is equal to a plus root b, which implies x minus a is equal to root b, which implies x minus a square is equal to b. Or let's do one thing, let's keep it as square root and make it square, which implies x minus a square minus root b squared equal to 0. Now, which means if we divide fn x by x minus a square minus root b square, we should again get a factor and of course a remainder if available. So let q be the quotient and r x plus r prime be the remainder. So therefore fn x is equal to x minus a square minus root b square times q plus r x plus r prime. This is the remainder part, this is the quotient part. Okay, so now this can be written as this is square, a minus b, a square minus b square is a plus b, a minus b. So this can be written as x minus a plus root b times x minus a minus root b quotient plus r x plus r prime. Okay, now this implies that fn of a plus root b, because this is the root that is given to us, is equal to, we substituted a plus root b minus a plus root b, a plus root b minus a minus root b times q plus r times a plus root plus r prime equal to 0, which implies if you notice here, a cancels, root b cancels, so we are left with a plus root b is equal to, this will become 0, so 0 plus r a plus root b plus r prime equal to 0, which implies that r a plus r root b plus r prime equal to 0, and we can write this as r a plus r prime plus r root b equal to 0. That means what? This has to be equal to 0 and this has to be equal to 0 for the remainder itself to be 0. So r root b equal to 0 implies that r equal to 0 since b is not equal to 0 or a perfect square. Remember, that is a condition that is given. So which means r a plus r prime equal to 0. Now r is 0, so this is 0 plus r prime equal to 0, which means r prime equal to 0. Therefore remainder is 0. So we can write fn x equal to x minus a plus root b times x minus a minus root b times the quotient is equal to 0, which implies that fnx is equal to 0 when x is equal to a plus root b and x is equal to a minus root b. Therefore, a minus root b is a root of the equation fnx equal to 0, right? So, very important. And that's it for now. Bye.